And with my great pleasure and big honor, let me introduce our next speaker today, Vasyl Ustimenko from the Ural Holland University of London, England, who will tell us about on geometrics over diagrams, symbolic computations, and their applications.
Okay. Thank you, Oksana, very much for presenting me. I just would like to share the screen. Okay, I hope you see my slides, yes? Okay, great. It's a great honor for me to take a floor and speak at this Ukrainian conference, which prove the resistibility and unbreakability of strong Ukrainian algebraic community. And other thing that the whole sequence of these conferences is just a central event which keep the vibrant and very influential international community of algebraists. So it's next step to keep it. So thank you very much. So the title of my talk was announced on geometries over diagrams, symbolic computation and their applications. In fact, the talk is dedicated to wide class of analogs of geometries of Chevalier group. New object will be defined over arbitrary commutative ring K with unity. Additionally, the temporal version, i.e. time-dependent incidence systems, will be introduced. I just keep these things. Okay, great. So I can move further. So the purpose to introduce new incidence structure in the case of finite ring K and corresponding multivariate ring K x1, x2, xn is their use in various algebraic applications to computer science. I will start with some applications to post-quantum cryptography, PQC. One of the fifth core direction of PQC is classical multivariate cryptography, which investigates option to use multivariate maps of small degree defined over finite fields FQ for the construction of public keys. So multivariate map is an endomorphism of FQ x1, x2, xn, element of so-called affine Cremona semigroup CS and FQ. Conventionally, each endomorphism F can be given by its value on variables. Just fxi is some multivariate polynomial fi x1, x2, xn. Written in their standard form, which is just the list of monomial terms given in its lexicographical order. We refer to the maximal number of non-zero coefficients of fxi as the density then f of f. The following multivariate transformation of the vector space is associated with the endomorphism F. It acts naturally on affine space. X1 go to polynomial F1 from this list of variable X2 to F2, Xn to Fn. And for the simplicity, we assume that the nonlinear F is a bijection. So the idea of public key is just straightforward. We have Alice, key owner. She has some magic trapdoor accelerator, which allows her to compute the reimage of this F in a polynomial time. And another part of the scheme, it's public user Bob. He uses standard form of F, just the standard form, to encrypt. And the knowledge of this T, private key of this trapdoor accelerator, allows Alice to decrypt in polynomial time. The security of this scheme rests on the sub-exponential complexity of finding the solution of the system f1 equal b1, f2 equal b2, fn equal bn. Okay, that's just general complexity. The security of algorithm of MEC actually can be reduced to the case when degree of f1 is 2. Actually, we can do some changes of variable and transform the system to quadratic one. So traditionally, MC multivariate cryptography uses systems of equations of degree 2 or 3 defined over the finite field. Despite the fact that the last talk on multivariate cryptography on Eurocrypt conferences was in 2021, many new results in this area were obtained, so one can look at proceedings of post-quantum crypt conferences 2024. Last one was in Oxford. And new crypto system by Jin Tai Ding, famous one. He moved to China now. His co-author Dieter Schmidt, plus 9 Chinese co-authors. So this soccer team presented this new crypto system for certification to National Institute of Standardization of USA. Okay, I just have to say that the construction of candidates for multivariate cryptography of small degree is not an easy task because the adversary can take various tuples P1, P2, Pn from a fine space and get corresponding value Fp, so he or she may use this information for the approximation of F-1. This is a rough idea of cryptanalysis. There is quite a big list of already broken quadratic crypto systems because if it's possible to design that, very often other people working can break the crypto system. Note that the complexity of encryption with quadratic map is O n cube. So what our proposal here? So we are going to work to substitute multivariate, consider multivariate map not only over fields but over rings. So develop some kind of case theory of multivariate cryptography. And the existence of zero divisors makes, of course, the problem of solving nonlinear equation is harder than in ordinary case. So we are able to create the public rules with of density O and E, where E between 2 and 0, of degree O1. So it could be any degree. It in fact doesn't affect the complexity, such that the action of F on the space of plain text Kn is a bijection. The knowledge of a private key, we actually working on private key, allows to decrypt in time O n square. So such systems can be, crypto system can be of interest and actually case, say, degree D equal 100, 10 hundreds, and whatever, actually are feasible cases, and we can take some popular rings like ZM, arithmetic modular M, in cases M equal power of 2, that 264 we have double precision arithmetics, so they are convenient for practical use. Okay, the complexity of encryption for public user is ON1 plus E, so it's better because E less than 2, it's better than in the case classical of quadratic equations because their complexity is cubical, ON cube. So that first is case theory. Second, idea to create a public rule F from end K x1, x2, endomorphism of this multivariate ring of density O1 and degree On, which maps K star n to Kn. Here, K star stands for multiplicative group of the ring, and the map must be injective. So the space of plain text here, we are encrypting elements of K star n, and the space of potential ciphertext is Kn. The knowledge of private key, this multivariate trapdoor accelerator, allows to decrypt in time O(n) square. So actually, because we use K star, the degree is a linear function from On, and actually the product, we can take the product of n and the order of multiplicative group, that's the maximal parameter of the degree possible in this scheme. And so it's kind of interesting crypto system, quite new. And that's some idea on multivariate cryptography. Other stuff is non-commutative cryptography. Yesterday was a nice talk by Dmitro Savchuk presenting some protocols, so I skip this time. I just will mention some problems which are important for creation, for design of protocols. First one, conjugacy power problem. So we have some semigroup S, actually Cremona semigroup can be a so-called platform, and given two elements H invertible 1 and G together with D, we are looking of equation Hx Gy H minus X equal D, and one can solve this equation for X and Y for the given D. So we are looking for family of semi-groups of kind generated by Hg, for which the problem will be NP hard. And candidates we choose, we can take the sub-semigroup of Cremona semigroup, which contains all elements of density O1 and degree O1. Okay, so we don't need to invert, so the product will be again density O1. And for each D, which is constant bigger than 1, we construct large non-commutative sub-semigroup SNDK such that maximal degree of its representative is D, and prove that conjugacy power problem is NP hard here. Actually, this is difficult task because if you have some transformation, say quadratic, and you're computing square, cube, and what power k, so those degrees are growing exponentially because we need to multiply generally elements, degrees of elements of affine semigroup. But surprisingly, there are analogs of the group AGL and K, where we have just D equal 1, and we are computing two linear things and getting again linear thing. That corresponding protocols are implemented. And in last thing that in 2018, in reports of National Academy of Science, I suggested the protocols of non-commutative cryptography based on navigation problems. So we need to find presentation of element from this S and K in the form of the word in given alphabet of generators G1, G2, GT. This, of course, harder problems than conjugacy power problem. And these platforms, those families of S and DK, are actually very convenient for implementation of these algorithms. Okay. So, and last trick, which is interesting, is that we are working in intersection of multivariate cryptography with non-commutative cryptography, as you see. So Alice and Bob can elaborate some, use some protocol and elaborate the collision element F. X from this semigroup S and dk. After take some polynomial map F, which has this trapdoor accelerator, and Alice sends F plus X via open channel to Bob, and Bob restores F because he knows X, just subtract, and can use this scheme. So here, this multivariate rule F in a shadow, because it's not given publicly. The security of entire schemes rests on the security of protocol. So it's similarly to situation like in national economic, we have public economy and shadow economy. Both are important parts of national economics, and modeling of shadow economics is nice topic of research studies. There are PhD theses on this topic in Ukraine. But here we have similar thing, task for cryptanalysts to investigate the option for adversary to break this shadow kind of public keys. So, and all these results, all these schemes are constructed in terms of special works on analogs on geometries of Chevalier group XMF. Here XM stands for the Dinking diagram, F for field, and we are just modifying these things. Instead F, we can take some finite commutative ring K. So it was kind of many international project, during the war we published several paper in Sprigge Nature. One is this conference, Future Technologies Conference in London 24, this restoration, it's about shadow type encryption. Other paper in a conference, Future of Information and Communication Conference. This is joint work with Pustovit. Alexander Pustovit, actually, he got the presidential award by President Zelensky for young researchers. This algorithm was implemented. Project with British colleagues, Professor Erskine from Scotland, James Tutte from Ireland, and Polish specialist Timoteusz Chojecki. So this is published in European Journal of Mathematics this year. A previous paper on this kind of when we have multivariate rule, it's in European Journal of Mathematics 23. And another just use of works on graphs or geometries for creating new secure stream ciphers, joint work with Timoteusz Chojecki, and last one is about public keys, joint work with Michał Klisowski and Timoteusz Chojecki. So now that's kind of results. Now our tools, just I need to mention some tools. I'm not going to give all details. So nice talk was by Professor Taras Banach about geometry, so I'm back to this topic. The incident system, accordingly, Hilbert is triple gamma IT, where I is symmetric anti-reflexive relation, simple graph on the vertex set gamma, and there is type function, gamma to n stands for type, n is some finite set, and alpha is incident to beta if and only if, and additionally, they equal the same time implies alpha equal beta. In case of cardinality of 2, people talking about incidence structure of bipartite graphs and use instead of incidence system. For instance, projective plane in talk of Taras Banach is incidence structure. Okay, now the bricks to construct the geometries of Chevalier group. We define Jordan-Gauss graph over K as an incident structure with partition sets P and L, isomorphic to affine subspaces V1 and V2 over K such that incident relation is given by special quadratic equation over the commutative ring K with unity such that neighbor of each vertex is defined by the system of linear equation given in its row echelon form. So this more formal definition. So we have points, some tuples of affine space x1, x2, xn, and y1, y2, yn stands for line, and brackets in parentheses allow us to distinguish points and lines. And x is incident to y if and only the following relation holds. So we have type SRM, so we have S variables here and R there, and after we need to add one variables x s plus 1 and another one y r plus 1. And continue this last equation looks like this. We have a list of variables up to s index s plus m minus 1 for x's and r plus m minus 1. Here ni and bi are not zero divisors. And fi are quadratic multivariate polynomials with coefficients from k, and we assume that the map sending pair x, y to tuple f1, f2, fm, like this, is a bilinear one. So, okay, we can think that fi given in standard form. This x1, x2, xs are colors. We have color space for points and color space for lines, because for each color we have just unique neighbor. That's the convenience of these graphs. And of course, linear equations in row echelon form allow us to compute things very effectively. So let's NAV is operator of taking neighbor of vertex V of color. Color is from KS, disjoint union with chi R. Another operator is jump operator, jump of color operator GA V, which just take V and recoloring its changing its color for color A, which is tuple from KS disjoint union KR. So the walk in this graph is uniquely defined by initial vertex and walk with jumps. And we are doing the following business, taking operator recoloring GA1, after operator taking neighbor, recoloring neighbor, and etc. So walk is such a walk with jump is uniquely given by the initial vertex and the list of colors. Now, okay, so I will go to definitions. First of all, we have group incidence systems. This here is group and family of subgroups GS. And here G is the abstract group and GS is the family of distinct subgroups. So we can take the all left cosets of GS, of G by GS, and two cosets are incident if and only if the intersection of them is not zero. The type function is defined T alpha is S when alpha is coset of kind GS, so defined by the subgroup. Okay, so we can take such geometry in case of Coxeter group. So here this Coxeter generators, I skip some details, and we have standard subgroups Wi just from as we need to skip one generator, get a family, and that's the geometry of Coxeter groups. Okay, and finally, we're going to this family of Chevalier groups. And here we what we use maximal parabolics. Here B-Borel subgroup we take Pi, BWI, P, and this group geometry is the geometry of Chevalier groups. Now, what is the connection?
So what is double WI?
WI, okay, so we have Coxeter generators. SI just selected generator and we skip them and generate by S minus SI. So it will be subgroup in Coxeter group.
Okay.
Just take out one generator and you get WI. That's the trick. Now, if we take the orbits of Borel subgroup on geometry of Chevalier group, then these orbits are naturally indexed by elements of Vasyl geometry because some connection with double cosets. And what we have, if we have incidence relation in Chevalier group, and we have two elements of Vasyl geometry, gamma and gamma prime, we are taking union of the classes B gamma and B gamma prime, and take restriction of I on this set, we get Jordan-Gauss graph. Some result, actually it follows from my results in Ukrainian math journal in 1991. But if gamma and gamma prime are not incident, then the restriction of I on this union is just empty set. So roughly we can think that geometry of Chevalier group is bunch of vector spaces because each orbit is vector space of kind B gamma, and a bunch of these Jordan-Gauss graphs given by selected for each gamma and gamma prime. Actually, they can be equations of them can be obtained via description in via root system of this group. So what is simple idea that we can just take out this that actually description I refer to talk of Taras Banach, that it's in fact generalization of whole ternary ring or whole sternar, as Korniakov said, just this generalization not for projective planes but for entire class of Chevalier geometries of Chevalier groups. So we can substitute this class and use the arbitrary ring K with unity and select the family of Jordan-Gauss graphs that GWK stands for selected family and get the geometry. And in fact, what we, maybe I just will simplify, I'm afraid maybe just comments that this generalization is interested even if we keep the field, because we are able to use the, to change the natural Jordan-Gauss graphs related to this geometry of Chevalier group for other one. So it's huge, actually, it's huge class of incidence systems. Okay, maybe I will skip the details in fact, some properties as holds if we don't care about which Jordan-Gauss graphs are taking. In any case, the incidence relation of this incidence system will be connected one. It's possible to prove. And even it gives a small word graph if we keep diagram xn fixed and k is increasing, like taking finite field fp and p running through co-prime numbers. So that's why this object are used in networking. And the idea is like this. We can take any field or any ring, K, and a very important ring for us is ring, multivariate ring Kx1, x2, xn. Yes. So the bridge is that we're taking the one Jordan-Gauss graph G alpha B of type RSN, where alpha and beta are Coxeter elements. So they contain Coxeter elements. And containing a round walk, we are starting from alpha, going via H beta in this Jordan-Gauss, going to other elements, and after through beta returning to alpha. So if we're doing this walk with jumps, and we can start with special tuple from this Jordan graph, which is just x1, x2, xs, xs plus 1, xs plus 2, xs plus m, and s plus m is n here, like in this geometry. So we are going to the last vertex from this walk, and coordinates of these vectors of this vertex G1, G2, Gs were this polynomial. And we are writing polynomial form x1 going to G1, x2 to G1, xs to Gs, and xs plus m to Gs plus m. So this is multivariate map. We can control degrees via choice of colors, get special semigroups, as I told, and special choice of color give us bijectivity if we need this one. So this is roughly the technique we use for our result we mentioned. And the list of colors, so-called color trace, is this magic accelerator that if f, say Bob knows only map f in standard form, but Alice, he can only encrypt, but Alice knowledge of this walk, actually colors of this walk allows her to decrypt in polynomial time. So that's a rough idea. And my just final remark, I'm not going to take more time, that my talk illustrates story of the transformation of pure algebras to the worker and applied algebra. Andriy Olinik and Dmitro Savchuk from our vibrant algebraic community also went through such transformation. Thank you very much for your attention. Slava Ukraini!